Thank you.
So the next speaker is Philip.
I was talking about sense.
So thank you. So this work has been done in Laboratoire FAST of Paris University in Orsay, and with a PhD student, Raphaël Fischer, Marc Rabot and Bernard Perrin from the École Normale Supérieure. And we are interested in the context where granular flows are so close to the solid-liquid transition so that we cannot be able to use the dense rheology that works well on steady state and some other unsteady state, but beyond the solid-liquid transition. So let us remind that a key article, which is the one from Bouchot, Cates, Ravi Prakash, and Edwards, that propose in '94 a now famous model, BCRE, which is based on some exchange laws from a static phase to a rolling phase. And with this model, they predict some relaxation of the slope angle during an avalanche event. And with this, for example, this flushing time of one avalanche event that is decreasing with the initial value of the slope angle. And they introduce two critical angles, the angle of repose at which the avalanche stops, and also another critical angle that is called spinodal angle. And this model has been modified in the following years by Pierre-Gilles Degène and co-workers, and used in many situations. For example, the slope relaxation of a sand step, so that they also predict some relaxation of the slope as a function of time, and also in some rotating drum configuration open here, where they predict some time variation of the grain flux that reach a maximum and then decrease toward zero with some different shape depending on the precise shape of velocity profiles that are considered inside the rolling phase. And in all their papers, in a given paper, they introduce the notion of the neutral angle as a critical angle, and at this angle there is an exact balance between erosion process and accretion process. And now I want to show you our experimental contribution to this context of how a sand pile relaxes by a simple avalanche process, and a natural avalanche process close to the critical angle of the pile. So we are using a rotating drum setup, half filled with dry glass beads of order 1 millimeter in diameter, and the drum is about 20 to 50 centimeter and a given width of few centimeters. And the drum is rotating at a low enough angular velocity, so that we are in what we call the discontinuous avalanche regime. So that if you look at the evolution of the slope angle as a function of time, you have this sawtooth appearance, so that the slope angle increases linearly with the angular velocity, so that the grains are at rest in the rotating frame, and then at a given angle, that is the starting angle, there is an avalanche process that makes the pile the slope of the pile to quickly decrease by an avalanche flow towards a stopping angle. And the difference between the two angles we call the amplitude of the avalanche. And these two angles are not perfectly constant, but there are some variations, and the advantage of the rotating drum is that we can make many avalanches, successive avalanches, and here are the distribution of the starting angle, stopping angle, and the avalanche amplitude that are roughly a non-zero value and roughly Gaussian distributed. But one key point is that when we plot the stopping angle, the angle of repose, as a function of the starting angle of one avalanche, there is a weak but non-ambiguous correlation. And with this correlation, it allows us to define a neutral angle here. That is to say, an avalanche that would start at this angle immediately stop at this angle. So an avalanche of zero amplitude. And now we can look precisely at the time relaxation of avalanche. So here are a zoom on these two avalanches. So there are two different avalanches of two different amplitudes. So what we see here is that an avalanche that starts at a high angle goes to a lower angle, as we see in the previous correlation here, negative. And the opposite for the smaller avalanche. And what we saw also that the avalanche time for the avalanche is smaller for a higher amplitude. And we can superpose these two avalanches by adimensionalize the slope angle and the time by the avalanche amplitude and the typical time of amplitude. And we can make this for all the many avalanches we have recorded, 300, more than 300, and we have this sort of master curve which is close to a half Gaussian curve, and there is a very well-defined master curve for this slope relaxation. And now we also show that there is a correlation between the time duration of avalanche and the amplitude of the avalanche. So the avalanche are shorter in time when larger in amplitude. That is rather non-intuitive, and our explanation for this is that avalanches behave as a free fall along the length of the pile, which is the radius of the diameter of the cylinder. But this free fall is with an effective reduced gravity, which is the gravity times the avalanche, the amplitude of the avalanche, or in fact the deviation of the starting angle relative to the neutral angle of the pile, and not with the driving gravity, simply g times sinus theta. And now, how can we explain by modeling this experimental observation? So we consider now a thin layer of constant thickness but evolving velocity, and that is exactly the opposite of what is considered in the previous model developed by BCRI and PGG, which consider evolving thickness but constant velocity. And our consideration is based on our experimental observation, that is the velocity profile inside the granular flows is exponential, but with a characteristic thickness that does not evolve in time, but with an evolving surface velocity. And with some conservation of the mass and momentum, we can write some equation. So the grain flux here, that is roughly the product of the thickness of the rolling phase with the typical velocity, is in fact linked in our configuration to the time derivative of the slope angle with some geometrical parameter, which is the radius of the drum. And we consider also a simple momentum conservation that makes the balance between the acceleration of the layer due to a gravity term and minus a frictional term, which we express like this with a constant term at vanishing velocity, which is related to the neutral angle, and a velocity-dependent term of friction that is a given power n, and the existence of the experimental master curve of the slope relaxation as a function of time impose that here the power exponent of the frictional law is 2, so that we obtain this differential equation. These are acceleration and gravity minus the solid constant frictional term and velocity-dependent term, and which is writes in non-dimensional writing like this. And so, we can plot all this, and the avalanche starts as if the acceleration is roughly constant, so as a free fall, and if there is no dependent term of velocity, we have this curve. We would have this curve, which would be symmetrical with respect to the neutral angle, but this is not the case. And for obtain an asymmetrical curve, as in the experiments, we have to consider this term, and with this fitting parameter, we can estimate a dissipative length of the process. And we can also compare the time evolution of the grain flux of our experimental measurement by slope measurements, our PIV measurements with our model, which is rather close and rather different from what was obtained by BCRI and Dejean and co-workers. And now I would show you what is expected when the drum velocity is increased. So there would be certainly a transition at a velocity that we can expect at a given value given by the avalanche amplitude relative to the avalanche time, typical avalanche time duration. And with these experimental quantities, we expect this transition to occur at this velocity. But by which scenario? There is some experimental observations that show that there is some hysterical behavior, so that you are in the discontinuous avalanche up to a omega-1 velocity and then switch on the continuous flow regime, and when you decrease the velocity, you switch to the discontinuous avalanche regime for another velocity omega-2 that is smaller than omega-1. So this observation has been done by Raschenbach and the team of Douady and Fauve in the early 90s. But this is not at all what we observe. And we observe rather not at all an hysterical behavior, but intermittencies between the two regimes of discontinuous avalanches and continuous flow. And in a given range of angular velocity. Here you can see some bursts, little bursts of continuous flow regime where the angle is about constant as a function of time and not this periodic or quasi-periodic discrete avalanche regime in red here. And when you increase the rotating drum velocity, there are much larger, many events of continuous flow regime and much larger in time. And we can exactly know when the pile is in discrete avalanche or continuous flow, because when we look, it is not so clear in the slope angle as a function of time, but if you look at the time derivative of slope angle as a function of time, it's clear, because when the pile is at rest during the discrete avalanche regime, the time derivative of the slope angle is exactly equal to the angular velocity of the drum. And when you plot the time derivative of the slope angle as a function of the slope, you can observe these loops that are characterizing the discrete avalanche regime. So no motion and then avalanche flow and so on, or continuous flow, that is normally with no noise it would be a fixed point, but there is some noise, we will see. And this was for minus than 1 minute. For few minutes this is this, and more than 3 hours this is this. So we have two attractors in this system, one fixed point corresponding to the continuous flow regime, and a limit cycle corresponding to the discrete avalanche regime. So now we have also recorded the fraction of time in the continuous flow regime. So we are just in the discrete avalanche regime, and then we jump to the continuous flow regime when the angular velocity of the drum is increased, and we jump, but gradually and not hysterically, with a tangent, hyperbolic tangent curve. Indeed, if we look at the distribution of lifetime of all the bursts of regime, of each regime in the other regime, we can observe that the distribution are Poisson laws, follow Poisson laws, exponential, decreasing exponential. That is more clear here when we plot the cumulative probability. And we can extract so a mean lifetime that depends on the angular velocity. So the mean lifetime of the discrete avalanche regime is large at low velocity and decreases at large velocity, and the inverse for the continuous flow. And we can say that, okay, we are at the middle of the transition here, and the fact that these follows exponential laws makes this hyperbolic tangent curve. And also that suggests that this is a noise process, noise-induced process. And so we took the model and adapt to a non-negligible, the model that I presented to you just before, that works for the avalanche flow, so when the grains are flowing. And we just had this term as now the angular velocity of the drum is non-negligible, and we add also Langevin random terms of Gaussian white noise with zero mean, and in the static term just write this and predict that flow starts at a given angle, and the model can reproduce the experimental observation. And here are the avalanche, and the fact that there is a non-zero bay makes that we can, if the angle, if the avalanche starts below this dash line, it goes to the continuous flow regime. And this dash line depends on the position of this dash line depends on the angular velocity of the drum. So you can switch on the continuous flow, and the critical velocity is just governed by the distribution, experimental distribution of the starting angle. And also the model predicts that with some noise term, you explore some zone around this point with zero noise. And in fact, the continuous flow is always stable and is just destabilized by the presence of noise level. And now, two remaining questions. And so the model can reproduce, in fact, either hysterical or intermittent transition depending on the noise level you have. Because as omega 1 does not depend on the noise level and is roughly can be considered as a constant, but omega 2 depends on the noise level. So when omega 2 is below omega 1, you are in the hysterical regime because each of the two regimes are stable. But when you are here at a sufficient noise level, omega 2 is higher than omega 1 and the two regimes are unstable. Just two remaining questions. What controls the noise level and what controls the distribution of theta? I just answer the first question. By measuring the noise level, by measuring the grain flux fluctuations. In the model, we can show that the fluctuation in the time derivative of slope angle, that is to say the grain flux, are proportional to the noise that we had in the equation. And we can just measure the grain flux fluctuation here that are roughly Gaussian. So we are just measuring the width of the distribution, Gaussian distribution. And we show that, in fact, experimentally, the grain flux fluctuations are increasing with the grain diameter. And we also show that the critical velocity, transition velocity, increases with the grain flux fluctuation, so that, in fact, the noise level is governed by the grain size, or, in fact, the ratio of the grain size to the ratio of the pi length. And the critical velocity for the stability loss of the continuous flow regime is, in fact, found to be experimentally governed by the intrinsic noise level, so that by this observation. And just concluding by saying that this sort of intermittent behavior between two regimes are also observed in different physical phenomena and are characteristic to a sort of subcritical bifurcation induced and in the presence of noise. So we can have hysteresis, hysterical behavior, or intermittencies, and we observe this in solid friction. The solid of you have stick slip or continuous sliding, and you can switch from one to the other, or peeling of adhesive tails, crack propagation, stop and go, or continuous propagation, or even von Karman flows, explaining the reversal time dynamics of the magnetic field of the Earth. So thank you for your attention.
Questions, please.
Do you think the filling ratio of solid in drums affect the transition between the discontinuous to continuous regime? I mean the filling of the filling ratio of particle in a drum, maybe 50% or 40%. Do you think it will affect the transition?
I don't know if I understand the question, but there is some.
I mean, in drum.
Yeah.
If you fill particle into a drum, the filling level is different.
The drum is just half filled with particles.
If it were different to half filled, how would things change?
Yeah, how it market that?
We don't look at that, so I think it would perhaps changes some the critical velocities or some. But I don't know if it changed dramatically the
D over R gets changed to D over R.
Okay. Yeah, we can change by this or just by change by the size of the drum.
Just one more question.
Yeah, but the question, okay, would be related in your crucial hypothesis that lambda is independent of the time and it's the velocity, which depends on the time. It works presumably very much better when when the drum is half filled, or not?
I don't know.
Okay, if we could thank Philippe and all the speakers in this session. Just a reminder about the trip again, so 1:45 to 2, maybe by